Log on, tune in, find out. Another good idea from Cambridge.
Go ahead and start. So welcome to the first post-instructional workshop seminar. So I guess we'll generally meet on Tuesdays and Thursdays, and there's going to be another talk this Thursday. Next week, there's a talk on Thursday. There's nothing for next Tuesday right now, so if someone wants to give a talk and wants to just volunteer, just let me know, and I can put you down for next Tuesday, or later also. And then I think later in the afternoon we'll meet and go out for a drink or something. So if you are interested in coming along, we'll just meet out in front of the reception area at 5:30. Okay, so it's my pleasure to welcome Anton Cox from City University London, who will tell us about blocks and decomposition numbers for the Brauer algebra.
Thanks so much for the opportunity to speak. What I want to do is outline some results about the Brauer algebra, mainly concentrating on the results and not the methods, to give a flavor of the kind of mathematics you can do in these kind of algebras, and perhaps try and convince you that they belong to a class of algebras that might be worth studying. So Brauer algebra can be regarded purely combinatorially, but people often draw a graphical version of it, and you can think of it as one of the many examples of a diagram algebra. Lots of diagram algebras are studied. They're introduced in a rather ad hoc kind of way, mainly in mathematical physics, and I want to suggest that quite a few of them can be described in a way whose combinatorics looks rather like what we've been looking at in Lie theory last week and the week before. So I mainly want to talk about the way you might want to represent the answer to various problems rather than the way you might prove what the answer is, and try and translate that representation of the answer into something more Lie theoretic. So they arise, as I said, mainly in mathematical physics. It's the progenitor of many of the graphical versions. Often they're Hecker algebra quotients, which is one reason why you might expect them to be maybe Lie theoretic. Sometimes they're not. But we're only going to look at essentially one example today, maybe two, depending on the time. I want to mainly concentrate on the Brauer algebra, very classical object, introduced, I guess, almost 80 years ago now, and a variation on it, the Brauer algebra, which is very similar and I might not say very much about at all. And these don't arise, you would have thought, in physics, although there are speculations they might, but they mainly come from invariant theory, so I'll briefly sketch where they come from, what they look like, and then talk about their representation theory. The stuff that's new is mainly work with two authors, Maud de Bischer and Paul Martin, a variety of papers. If I get time to talk about it, the Brauer is the same set of authors with Steve Doty. And the combinatorial framework I'm not going to describe, which we kind of used to study it, was introduced with Martin again and Parker and Shi. So that's the background. Now perhaps I should say a few words about what I mean by a diagram algebra. So throughout this talk, I want to fix a field, and uncharacteristically for me, it may well be the complex numbers, the perfectly good field to work over in this setting, and it typically will be for most of the examples we actually want to talk about. And I'm going to fix a parameter in that field, which, for simplicity, I might choose to be non-zero for now. I could get around that problem if I was more careful, but if you want to be careful, you might just assume it's non-zero for the moment, then there's no problems. And diagram algebras are not well defined. They're basically given by some kind of graphical calculus, and then there's variations of the kinds of graphical calculus you might allow. And so I want to merely describe an example of the kind of thing that one might want to do. So for me, in this talk at least, a diagram just consists of a rectangular frame with some distinguished nodes on the top and bottom, the same number of each, which I'll call the northern nodes for the top and southern for the bottom, and they'll be connected together by some configuration of lines. We could connect them by other objects, but let's just connect them by lines for now. And the way the algebra is going to be determined is by writing down what the allowable configurations of lines are, and then discussion of how to multiply diagrams. So there are lots of different ways you could do this, and you'll see for an example, the typical kind of example of how they might be done, but there's a variety of other examples I might mention in passing. And for any such space, we're going to typically have a finite number of allowable diagrams, which will form a basis for the algebra. So this is very much like the group algebra of a finite group. We take the group elements to be basis elements, we have linear combinations of those. We do the same with diagrams. take linear combinations, and all we then have to describe is the multiplication on diagrams, which, as it's going to be linear, we can describe just by describing how to multiply two individual diagrams. And again, that might vary from algebra to algebra, but if it's going to be a diagram algebra, it should somehow make use of the diagrammatic representation or realization of the elements in some ways. So the easiest way to multiply two of these diagrams, they have distinguished vertices at top and bottom, is to draw one above the other, ignore the middle line of vertices, and then have a new diagram which consists of the concatenation of the two that you started with. Typically, though, if you just multiply diagrams like that, you won't get a diagram in the allowed form. You'll see examples in a minute, and certainly if you don't restrict the kind of answers you get, you'll almost certainly get an infinite dimensional algebra, because you'll get infinitely many independent diagrams possibly arising out of repeated applications of this procedure. So the only relations essentially we're going to impose are ones that will reduce our diagrams to the allowable form, which more or less only really ensure that it's finite dimensional. There are other reasons for choosing the particular ones we look at, but as far as we're concerned, we can regard them just as some kind of finite dimensionality constraint. So the only real example we're going to need to know, the Brauer algebra, is not really very diagrammatic, because the description of the allowable diagrams doesn't involve very much of a picture. It just says each node is connected to precisely one other. So we'll draw the connections by lines. The lines might go from the top of the diagram to the bottom, or they might not. And of course, if they only went from the top to the bottom, we'd just be looking at a realization of the symmetric group, which is not a very diagrammatic algebra. We'll regard them as equivalent simply if they have the same pairs of connections. So we're only really interested in the pair partitions of a set of 2n points. And the product is going to be by concatenation, but now we have the problem we might get a closed loop. And obviously, once we've got one closed loop, we can repeat the process and get infinitely many closed loops, or arbitrarily many closed loops. So we're going to need to remove those to make this finite dimensional. And the easiest way to remove them is just to remove them, and at least keep track of the fact they've gone by putting some scalar parameter in front of the product of the diagram to keep track of how many loops have been removed. So we're going to multiply the diagram by our fixed parameter delta, which I chose in my ground field. So here's an example of two Brauer diagrams. So on the left, we have one diagram. I want to multiply it by the one on the right, and multiplying left on right means I just draw the left-hand diagram above the right-hand diagram. Now, if you do that, you'll see, I don't know how well you can see it on the screen, that there are some red arcs indicated on the bottom of that, on the top of this. If you join them together, you get one single loop. So we have a single copy of delta. There are no other loops in the diagram, and it's easy to check that if you trace, for example, this line here, appended onto that one, just go straight down, and all of the other ones match up in the way that you can check across the screen. Clearly, it's obvious in this kind of case, the top half of this diagram must be the top half of this one, the bottom half of this one must be the bottom half of this one, and all that you need to work out is where the lines that go from top to bottom actually match up. And although I'm not really going to talk about it, that's kind of a trivial reason why these algebras are always cellular, because those are your half diagrams, your half tableau. I don't really want to say very much about that, but these algebras are designed to be very easy to compute with. You often have one-sentence arguments about why certain properties hold. Properties are often rather more difficult if you're looking at something more complicated like the symmetric group. Of course, we do have the symmetric group here because we can look at just the lines that propagate from top to bottom. That's a subalgebra. It's not very useful to have a subalgebra. It's also, as it happens, a quotient algebra, and that will be key to what we do. But this algebra has a number of advantages over the symmetric group that we'll see as we proceed. Very briefly, just in case we use it later, the Brauer algebra is essentially just a subset of the diagrams you use for the Brauer algebra. We're just going to draw a wall in the middle of our diagram, which I put a dotted line to represent, and we impose the extra rule that any line that goes from top to bottom cannot cross the wall, and any line that doesn't go from top to bottom has to cross the wall. So all the arcs on the northern and southern edges have to cross, and all the ones that go from top to bottom can't. Clearly, if we take only lines that go from top to bottom, we get two disjoint copies of permutations, so we're going to get a product of two symmetric groups. And if I choose to have R nodes on the left and S on the right, then that'll be SR cross SS. So the Brauer algebra's representation theory will be closely related to that symmetric group. The Brauer will be closely related to the product of symmetric groups, and we'll see a bit more about their structure as we proceed. So why study them in general? Individual examples might be interesting, but why study any other examples? So I've already said some of the areas where you might see algebras drawn graphically. And perhaps the most obvious place which you find in the literature is in algebraic statistical mechanics. The Templey-Lieb algebra, which I didn't mention, is the one that's perhaps best known as a diagrammatic algebra. That's merely the Brauer algebra with the extra relation imposed that you can't allow strings to cross. So that's a truly diagrammatic algebra because you can most easily see the relation on which pairs can be joined by drawing a diagram. And indeed, a planar algebra, one where the strings can't cross, often has a very strong graphical calculus simply because you've got the planarity, which is a strong constraint. So in that sense, the Brauer algebra is not very diagrammatic. It's more purely combinatorial. There are lots of variants I won't talk about, mainly mentioning them to show that there are many others that we can approach in a similar way. And there is some suggestion that the Brauer algebra may have a role to play in physics and conformal field theory, but probably not. Perhaps more interestingly to this audience is that you can often represent affine or ordinary Hecker algebra quotients as diagram algebras, at least the very low rank ones. The Templey-Lieb algebra is an obvious example. And the blob algebra was introduced with Graham and Martin partly to understand the representations of the affine A Hecker algebra, the two-step nilpotent representations, and work out their decomposition numbers. So you can learn some interesting things about affine Hecker algebras. But the link I want to mention in this talk, although we won't actually use it very much, is invariant theory, which is what motivated the definition of these algebras and maybe inspires the form of the answer we want to give at the very end. So we don't need very much about it, but let's just remind ourselves of something that I'm guessing is probably fairly well known to people in this room, Schur-Weyl duality in the classical case. So we'll take the natural representation of GLN, n-dimensional space with the ordinary matrix action. Of course, once we have the action of GLN on V, we can take the action on any tensor power of that. So we'll take the R-fold tensor product of V with itself. That obviously has an action by the group, but we can also now permute the tensor factors, the order of the tensor factors, and that gives us an action of the symmetric group. We can talk about what's the relationship between these two actions. So Schur-Weyl duality is just the observation that if we look at the space of all linear endomorphisms from the tensor space to itself, and consider those ones that are morphisms for the symmetric group or morphisms for the general linear group under this action, then the image of our two actions, the image of the general linear group in this endomorphism space or the symmetric group, is actually precisely the endomorphism algebra for the other group. So if we want to know, this is a double centralizer property. Basically, each action centralizes the action of the other. And if you use this in either characteristic 0 as Weyl did, or in characteristic P, as is done perhaps more frequently nowadays, you can use this relationship, this very close relationship, to transfer representation theoretic data from one side to the other. You can study the general linear group via the symmetric group or vice versa. And so this is a long-standing and well-used tool for relating those two representation theories. And all the Brauer algebra is really is a way to generalize this relationship to other classical groups. That's the motivation for Brauer's definition. Of course, we're only going to get a quotient. There's nothing here that says any of these maps are faithful. We'll only see maybe a quotient of each side. We won't see the whole of the symmetric group. We won't see the whole of the general linear group. So we carve a portion out of each representation theory and relate those. And maybe if we vary R, we can do something about that. But that's not going to be something I need to be greatly concerned about. We just need to bear in mind these aren't images of the whole group algebra in this endomorphism algebra. It's just a quotient in general. If you did this with quantum groups and you only looked at GL2, then you'd be taking a quotient of the Hecker algebra of type A, and that's precisely the algebra that's the Templey-Lieb algebra. So that's one sense in which we already have an example of a diagram algebra which comes in some kind of Schur-Weyl duality. So the Brauer algebra, as I said, was introduced to deal with other classical groups, and it deals with two at the same time. It deals with the symplectic and the orthogonal groups. And so we're going to have a parameter in our algebra, which is going to be labeled delta in this talk, and somehow varying this parameter will allow us to deal with all the symplectic and all the orthogonal groups by suitable choices. So we just repeat what we did for the general linear group, take the natural representation either of the orthogonal or the symplectic group, ON or SP2N, in my labeling scheme. We'll do this over the complex numbers for simplicity, although there is a version of this in positive characteristic. And Brauer defined an action of his algebra on tensor space. We don't need to care about what it is. He just explicitly wrote one down so that if we looked at the image of each action, then we got the same double centralizer property. The image of each is the set of endomorphisms that commute with the action of the other. So what he did was he had a single algebra, and he varied the parameter so that if it was a positive integer, as in the top line, then we got the orthogonal group, and if it was a negative even integer, he gets the symplectic group. But this makes perfectly good sense, this algebra, BR, for any value delta in our ground field, so we can study it for non-integral values of the parameter, or indeed odd integers, negative integers. And it's a perfectly well-defined algebra, and we'll see that the representation theory is essentially uniform. We don't need to care about the various cases, orthogonal and symplectic. We're going to have a single way to describe the answer that will cover both simultaneously. So this is going to be the motivation for studying the Brauer algebra. One motivation is to try and understand this representation theory. But it's not going to be a very good tool for us to actually use, because I'm going to be working in characteristic 0, and in characteristic 0, all of these groups on the left-hand side have semi-simple representation theories, so there's not very much to do. Whereas on the right-hand side, the Brauer algebra doesn't. It's typically not a semi-simple algebra for small choices, small integral choices of the parameters. So all we see in this duality is some kind of semi-simple quotient. So we're going to not be able to transfer information by a Schur-Weyl duality. Instead, what we're going to do is transfer an expectation from Schur-Weyl duality that there should be a combinatoric coming from orthogonal or symplectic Lie theory, which will describe the answer. Again, just quickly, in case we have time to discuss it, the reason the Brauer algebra, which looked rather arbitrary, was introduced is because there's a similar Schur-Weyl duality. Now for the classical general linear group, no other types, but changing the tensor space. So we've got the natural representation of GLN. We can also consider its dual representation. And now if we take a mixed tensor product, some number of copies of the natural space and some number of copies of its dual, then there's an action of this that can be defined with the Brauer algebra, and this centralizes the action of GLN. So we have a type A version which isn't classical for the Brauer algebra, corresponding when we take one of the parameters R or S to be 0 to be a generalization of the action of the symmetric group and type A. None of that's really going to matter because we're not going to use it, just to motivate why we might want to study these algebras. What might we want to know about them? Well, as far as I'm concerned, for the purposes of this talk, understanding the representation theory is going to mean hopefully answering something like the following list of questions. So the simplest question we'll start with is, what is the block structure of these algebras? So what's the equivalence relation generated by non-split extensions of simples? Can we describe the blocks? We'll see that's not so hard to describe. These algebras fall into certain natural classes. We'll talk about them in a minute, but basically they have certain naturally occurring modules, which, as always in any theory of this kind, are easy to construct. They're going to be standard or cell modules, which we can explicitly write down, a basis, as it happens with diagrams, and an explicit action. So we can understand anything we want by brute calculation about these modules. And having, of course, in general, they won't be simple. And having a family of such modules, which one for each simple, in fact, we're then going to hope that we can construct enough information from them to understand the simples indirectly by working out the multiplicities of simples in each of these standards. Exactly as you would in Lie theory, if you could understand the decomposition of standard representations into simples, then as there's some kind of lower triangularity property on the ordering of the simples, you could then infer from that the characters of the simples and dimensions and anything else you want to know of that nature. So all I really want to know to understand these modules is to understand how the standard modules that I'm given from nature break up or have filtrations by simple modules and describe the multiplicities arising in those filtrations. And that's the question I want to finish by answering at the end of the talk. Now, I said these algebras arise, not necessarily the Brauer algebra per se, but diagram algebras arise in physics, and in the physical motivation, there are strong reasons to believe the answer should essentially be independent of n. If you're looking at a physical model, n is usually, the reason why it's a diagram is you're thinking of a line of atoms. You're doing some kind of two-dimensional statistical mechanics, and the number of atoms in your model is one of the parameters, n, but you're trying to find a bulk behavior of some solid, like its melting point, or its conductivity, or its magnetism. And that shouldn't depend on the size of the object, so there should be a way to kind of take a limit that then gets very large, so Planck's constant large, which is independent in many of the things you're trying to measure of the actual variable n. So we're expecting the answers that we get to somehow stabilize. As soon as they make sense for the n we're looking at, they should remain constant for all larger n. And if we wanted to, we could kind of work in some kind of limiting sense and try and understand a limiting algebra, an asymptotic representation theory. And I don't want to say anything about how we might actually do the analysis, except to say that it's elementary. There's nothing hard in what I'm not going to tell you, particularly as we're working over the complex numbers, because all we're going to do is use explicit calculations. We have bases and modules. It's in the spirit of, say, the kind of James approach to representation theory. You've got explicit representations, explicit actions on explicit bases, so you can do some computations. Not very hard computations, but special cases. And that's the hardest thing you have to do. We then use the fact that there's plenty of symmetric group structure in here, so we use standard results about the representation theory of the symmetric group. And since we're working in characteristic 0 for most of this talk, that's very classical and easy. And then we have to have some way of organizing the data into some kind of inductive process. And there are natural inclusions of one algebra in the other just by adding an extra string. And there are other ways of relating our algebras which we don't have in the symmetric group by certain idempotents, which I might come back to in a minute. So we have a variety of ways of going between different values of n, and we're going to work by induction on n and try and inductively describe the structure of our algebras by making them larger and larger, and appealing to the fact that this result should be stable with n, so somehow this process should be a natural one to do, and that's also very straightforward. And then we need some general formalism for setting this all up and having our standard modules, and depending on the choice of parameter, it will typically be quasi-hereditary in characteristic 0, except for delta equals 0, and in positive characteristic, it won't be. It will be cellular. But these are both very nice theories. They provide you with a machine that can get you started, a very elementary machine. So if you use that kind of terminology with the kind of combinatorial bookkeeping that I've listed on that slide, basically you then go away and you do a little bit of combinatorial work to try and understand what's going on. And although it can get a little bit intricate, it's not difficult. The main thing I want to talk about is not how to do what we're going to do, but how to describe the answer. So once you've got the machinery to work out the answer, you of course need to decide how you want to express it, and that's perhaps the most interesting part of the problem. So mainly I'm going to talk about how might we write down the answer for these algebras in a way that tells us as much as possible about their structure. So I don't want to go into any technicalities about them. Quasi-hereditary algebras are basically Lie-like. And in characteristic 0, that's more or less what we're looking at. So we have something which should have some kind of Lie theory. In characteristic P, we don't. It's more like the symmetric group, which is not so well behaved in characteristic P. But cellular algebras are a way of generalizing that. Cellular algebra is a symmetric group-like algebra, and much of what we want, the rather elementary level we're working, these two theories provide in equal amounts. So it doesn't really matter too much for what I'm going to say, whether we're working in the highest weight theory setting or the cellular setting. We have enough of a machine to define some nice modules and look at their representation theory. And so we might want to introduce a labeling scheme for modules which we might refer to as weights, as we would do in Lie theory. Just very briefly to say something about how we might then organize the data. Towers of Ricamo with the elementary combinatorial description we wanted to use to organize the inductive step. And all this says is that for diagram algebras, we often have two very nice compatible ways of relating different algebras. And maybe it would be worth drawing a picture. So if I have almost any kind of diagram at all, any kind of algebra made of diagrams at all, it probably contains the identity element, which is just all the lines going from top to bottom. And so if I have any kind of diagram at all in my algebra with some number of nodes along the top, I can embed that diagram into a larger algebra just by adding an extra line from top to bottom. So there's an obvious algebra embedding. But if we've got strings and we're allowed to move them not just from top to bottom, there's a perhaps nicer way of relating representation theories, which is not to embed our algebra in that way, but instead to consider, well, that's the way I do it, some kind of diagram like this, which as long as it's in our algebra, is almost certainly going to be an idempotent. If we multiply this diagram by itself, we get up to scalar the same diagram, so we can divide by that scalar, and as long as we're not dividing by 0, this will be an idempotent. And it's an easy exercise in any kind of sensible diagram algebra to show that this idempotent induces isomorphisms between the algebra on n strings, with e on each side, and the algebra 2 lower. And then, in any sensible diagram algebra, this operation and the algebra inclusion are highly compatible we have essentially 4 functors, induction and restriction. We have the idempotent multiplication to go down 2 layers. We've got the right inverse of that, globalization, to go up 2 layers. And in any sensible diagram algebra, these 4 functors behave very nicely. For example, the induced module is just the restriction of the globalized module. So we never need to induce. We can always use the other 3 functors to relate them as long as we have certain technical conditions. And the only other thing introduced in this formalism, as we set it up, was merely some kind of locality constraint, which told us that when we did induction and restriction, modules which were nice to start with, like standard modules, should have a standard filtration, and the labels should somehow be close in some metric which naturally corresponds to the ordering of the algebras. So this was just a way to make the bookkeeping easier. The key constraint was that the 4 functors we have, induction, restriction, the idempotent localization, and its inverse, which we call globalization, were somehow compatible. And then you just proceed by induction and some careful bookkeeping. What quasi-hereditary algebras don't do, and certainly cellular algebras don't, is give you a combinatorial description which you have in Lie theory in terms of orbits. So normally in Lie theory we have some kind of highest weight theory, and then we describe the answer in terms of the orbit of a Weyl group on something, or an affine Weyl group. So we'll take some Cox group, some Weyl group, and we'll do something with it. These aren't encoded in the formalism, but we often have them lurking in the background anyway. Many of the algebras I've mentioned or not mentioned have a combinatorial answer which looks like it should be described by orbits. And that's how we'd like to state our results about the Brauer algebra. So in order to do that, I just want to quickly remind you what kind of language we use in such a setting, but I won't spend a lot of time on it because it's just entirely what we know from algebraic groups or Lie algebras. So I'm just going to talk about weights that are going to be elements of z to the n. And the key things we're going to need later are, if we're looking at an algebraic group, say, we have an associated Weyl group and it acts by reflections which fix the origin. We don't really care the precise form at this moment in time. And that's not usually the right action in positive characteristic Lie theory. You normally have to shift the origin somehow to make all the combinatorics work. So we have a nice reflection group action on some lattice, which preserves the lattice, and we shift the origin of that reflection group action to some other point, which is classically called rho or minus rho. So we have the same normal reflection action, but now we've fixed a different point, not the origin, and we call that the dot action of the group to distinguish it from the original naive reflection action. Now, if we're just taking the Weyl group, this action, and we could extend it if we wanted to the real space, R to the n, and if we do that, we can look at the connected components, and since we're looking at just the Weyl group, these are quite large, so we might as well call the connected components chambers. And then if you pick a labeling for, say, simples or standards or any other kind of natural class of modules in Lie theory, you find you don't need to use all weights, but only the dominant ones, which are those in some chosen favored chamber. So rather than looking at all of the weights in z to the n, we pick a nice chamber in our reflection group action, and there's our space. So Ruben kind of told us all about this when it was last week. Now, if you're working in characteristic P, you have another nice group associated, the affine Weyl group, which is just the semi-direct product of this reflection group with some translations by P in the lattice. So this will give you many more reflections as well, because you can translate and then reflect and so on. And that's usually what controls something like the block theory of an algebra group. We can again look at the connected components of its action on real space. And we'll call these alcoves because they're going to be a lot smaller. So our chamber is now being split into many, many alcoves and the walls between them. There'll be lots of different kinds of walls or intersections of walls. And if we can understand that geometry, we can often find that that controls the representation theory, essentially, of the algebraic group. We would like to express all the answers for our algebraic group in terms of this combinatoric. And we essentially can. For example, in characteristic P, it's almost true to say, that's what the star means, that the blocks for an algebraic group in positive characteristic are given simply by taking the orbits of this action of WP, the affine Weyl group, and intersecting those orbits with the set of allowable weights, dominant weights. It's not quite true because some of these things can break up if we're looking at a Steinberg weight, but it's essentially true. If you look at most weights, this will be true, and it's certainly morally true. At worst, you get unions of blocks in an orbit. So essentially, orbits tell you the block structure of your algebra, the orbits of the affine Weyl group, and you have a parabolic subgroup of that, the ordinary Weyl group, which tells you which weights are dominant. So our representation theory is controlled by two groups, W and the affine version of W, WP, one of which tells you which are dominant weights, and one of which tells you which collections of dominant weights are in the same block. And that's how we want to describe the results for the Brauer algebra. So just a concrete picture. I can't draw any pictures for the Brauer algebra because we are not looking at any nice finite-looking rank of like 3. So here's the standard SL3 picture. So W is just the ordinary symmetric group on 3 letters, which reflects around the 3 bold lines. I've chosen this chamber on the right to be my dominant chamber, and I've drawn a set of the infinitely many reflecting hyperplanes inside there, and put some dots to represent the integer lattice. So for example, one of the blocks for SL3 in this case would be just the dots which are not on any of the walls, because they're the only ones in their alcoves. So from this kind of picture, you could then read off or give lots of data about your favorite representation theory for SL3. And it wouldn't really depend on the dots. One of the things we can do in Lie theory is stare at the picture and kind of ignore the lattice points, and all that should matter is which walls we're on, or which facets we're in, which alcoves we're in. It shouldn't matter precisely which weight we use. If we pick 2 different weights inside the same triangle, essentially the representation theory should be the same, and again, we'd like that to be true for the Brauer algebra. So, coming to some actual results, as I've already said, we can't use Schur-Brauer duality in this setting to determine the blocks or anything about the blocks of the Brauer algebra, because the groups on the left-hand side of my duality were semi-simple in their representation theory. So there was essentially no block structure. We could perhaps think we should look at quantum groups, but that won't help because they don't have the right duality. They're in duality with something else, the BMW algebras. So that's not really going to directly tell us anything about the Brauer algebra either. But instead what we're going to do is assume that we just had some kind of relationship and say, well, if we had such a kind of relationship, how would we describe the answer? What would the answer be combinatorially? And then we'll prove that that answer actually is the right answer in our setting algebraically from scratch, and at the end have to make sure that it actually fits the answer we were hoping for. And it really will be entirely independent of any duality. We're going to work entirely internally in the algebra. And for simplicity, I'm just going to assume that delta now is an integer, because it's been known for a very long time, I guess 50 years, that the other algebras are all semi-simple. That follows from our results very easily too, but it's maybe easier just to assume that delta is an integer for now. So there's been lots of work, well, not actually all that much work on the Brauer algebra. There was a flurry of work in the 80s and 90s by Hanlon and Wales, and eventually by Dorr and Hanlon and Wales, which for our purposes provide everything you need to know to understand the representation theory. For some reason they weren't trying to answer the questions we were, but if they'd wanted to, they could almost have done it just by what they'd written down. So we just took their results, refine them a little bit, extend them a little bit, and use them mainly to describe certain cases where we had standard modules with non-zero homomorphisms between them. They've got bases, we can write down actions, we can check whether certain linear maps are homomorphisms. It's a bit messy, but you can do it. Dorr and Hanlon and Wales have more or less done it for all the interesting examples we needed. We did a few more, and then we're slightly more careful than they were with Frobenius reciprocity, and cooked up many, many examples of homomorphisms between a large number of standard modules. If you know there's a homomorphism between 2 standard modules because they have, in this case, simple, whichever around it is, simple head, I guess in this case they were, that basically tells you that those modules will be in the same block. So we can link weights up into the same block by using homomorphisms. What we need to do is show that they can't be in the same block in the other direction to get any kind of block result. But that's always easy in this kind of setting, because all you need to do is find some kind of central element which acts by a scalar, and then show the scalar is different on different modules, and hence they must be in different blocks. Now, it's not hard to find a suitable element in the algebra which acts as a scalar. A little bit more care than Dorr and Hanlon Wales takes gives you a condition which says that 2 things can't be in the same block, and then you have to hope that the 2 conditions you have from the homomorphisms and from the central element calculations match, and if they do, then you know the block answer. And essentially they did. Brown had already shown that these algebras were generically semi-simple. Hanlon and Wales and then Wenzel had gone on to show up to the point of non-integral choice of the delta. And we don't really need to work over C. In general, we can work over an arbitrary field, and very recently gave a complete criterion for semi-simplicity, which again will follow from the theorems we have on the board, but it's a nice simple statement of when these algebras are semi-simple.
This K is characteristic 0, or?
K is any field, maybe algebraic, well, maybe infinite. So it was known over C by, well, it could have been known earlier than that paper, but the result was deducible from the literature, but hadn't been written down properly. So I don't want to say how to get the result. I just want to tell you the answer, and I'll first describe the answer combinatorially in the form that we got it, and then tell you a better way to describe it. So everywhere in sight there are symmetric group combinatorics in this setting because the symmetric group is a quotient of our algebra. If we take our algebra and we take an idempotent like this one, and look at the two-sided ideal it generates, if we quotient by that, then anything with fewer than n strings in it will get killed, it'll be in the ideal. So the only thing that's left is something with no strings that don't propagate, so you just get a copy of the symmetric group. So if you quotient by the ideal generated by that idempotent, you just get the symmetric group on n strings. And as is the quotient, you can lift all its representation theory to your algebra. And all the Brauer algebra is an iterated inflation of this process. You take the symmetric group on Sn, Sn minus 2, Sn minus 4, and so on. And this is some kind of cellular inflation in the language of Koenig and Xi. So really, you're just gluing together the representation theories of the symmetric groups for n, n minus 2, n minus 4, down to 1 or 0, depending on your parity. And it's the gluing together that introduces some cohomology. So we're going to take traditional symmetric group combinatorics, a Young diagram. We'll take the traditional way of dealing with it, talking about contents of boxes, and we'll just describe some combinatorics on that. So I'm going to take a Young diagram, which I'm going to think of as a series of boxes in the plane, and I'm going to take, for each partition, and I'm going to take two partitions, lambda and mu, and I'm going to assume that mu is actually a subpartition of lambda, so it's contained inside it as a diagram. If it is, then I'll call it balanced if all of the boxes in the skew that are formed by these pair can be paired up so that each pair has content summing to 1 minus delta. So you draw your two partitions, one inside the other, you ignore all the boxes in the small partition, and the ones that are left have to be paired up in such a way that in each pair, one of the boxes has content, say alpha, and the other one has the content beta, so that their sum is 1 minus delta. And that's a fairly natural condition. Dornhan and Wales had that not pairwise, they had it for the aggregate set put together, which is not strong enough. This is a stronger condition. Plus, they had a tiny quirk which looks like a quirk of the calculation. If you happen to do one of their calculations by looking at the symmetric group, it turns out that when delta's even, these boxes that pair are symmetric around some kind of diagonal, because the content was j minus I, so the content is constant on diagonal lines for a Young diagram, and the diagonal lines are symmetric about some central reflection point, and if delta's even, the ones that are symmetric can be adjacent. So you can end up with a picture that looks like either A or B. The boxes that you're pairing can either be paired side by side or they can be paired vertically because they're actually next to each other when they touch. And it turned out that when Dornhan and Wales did a calculation for just the two-box case, they found in the two-box case you couldn't have a single column of two boxes, just from some silly feature of the symmetric group combinatorics. And if you use Frobenius reciprocity, you can generalize that condition to say that you always have to have an even number of columns in this setting. So that's just some kind of quirk.
Are you drawing these in the French way?
I'm drawing these in the English way. These are just tiny bits in my diagram. So I'm thinking of I'm thinking of my partition, some enormous sketchy thing here, and as it happens, two boxes are the same, which sum up will be reflections around some lines, so any pair which match will sum up. And if I've chosen delta to be even, I might have my pair, it might be that my subpartition starts like that, but it might not. It might start like that. So what I'm drawing in these little ladders is the intersection of the skew partition with these pairs of boxes that match up. So this is just a tiny part of the skew partition, the boxes that have contents minus delta over 2 and 1 minus that number. So this is some arbitrary looking condition. You can have any number of rows you like, but you can't have an odd number of columns, which comes just from Frobenius reciprocity from some symmetric group quirk. But it's a condition, and it turns out that if you take this condition, you can then work with it. It's easy to work with combinatorially. And we do this not just for partitions of n, but n minus 2, all the other ones, because we said we're basically looking at all the symmetric groups put together at the same parity. And then the first theorem we proved in our first original paper was that if we have two arbitrary partitions of at most n in characteristic 0, well, let's say for simplicity delta is non-zero, then they're in the same block. Well, they may not be contained inside each other, so we'll take their common intersection. That will be a partition. Just intersect the two diagrams. The sub-diagram will be a partition. So that's now a sub-diagram of both, and we really require that sub-diagram forms a balanced pair with both lambda and with mu. So it's a simple combinatorial exercise to determine for any pair whether or not this holds. I don't want to tell you how we prove this theorem, except perhaps in passing to note this means that every block has a unique minimal element, because I can just keep intersecting them, and that will be a balanced pair. So the minimal intersection will be a balanced element with anything in the block. So there's a unique element, and that basically tells you how to prove the theorem. You just prove that any non-minimal element has a non-zero homomorphism to something smaller, and then characterize the smaller things and show there's a unique one of those in each block. So in that sense, it's a delicate Frobenius reciprocity argument and lots of bookkeeping to prove this theorem. So these blocks are quite nice. They have a minimal element at the bottom. Everything else can be calculated explicitly using this nice concrete combinatoric, but it's not particularly pleasant to try and conceptualize, because it doesn't, for example, give us any clue as to what we might expect in characteristic P. It doesn't give us any structural reason to understand where this comes from, or any other reason for believing we can understand representation theory of anything else. So it's not a particularly good way to write down the answer. As I've said, essentially, most of this was almost done by Doran, Hannon, and Wales. They certainly had a weaker version of the condition about pairing boxes, and they had a two-box version of our second condition. But it looks like an arbitrary combinatorial quirk, which just drops out of the analysis. We wanted a geometric description in terms of orbits, so we'll go away and give one. We now know what the answer is, so we can just try and find on that answer by hand, by calculation, some way of describing these blocks geometrically. And as long as we can make it match up, it's fine. That will be the level of proof that we use. Take the combinatoric, find another combinatoric, and check they give the same answers. So you have to think of various things. You have to think of a group, an action of the group on a space, if you're thinking about reflection actions. You may want to think about where the origin is going to be, and then you have to hope that you've got some kind of matching between the two answers. So we had the orthogonal and symplectic groups. Well, of course, that gives us two types to choose between. So we have a little thing, and we might choose type D vowel group. We'll take its natural action on z to the n, the weight lattice, as we would do in Lie theory. We already know that we can label our representations essentially by partitions, so why don't we basically do that? So we'll look at the set of weights which are partitions. We're choosing them. I mean, we're just choosing that labeling. And it's not quite as natural as it looks, but we won't worry about that. The hardest part, perhaps, is to work out where the origin should be. So let's just decide to shift our reflection group action, the W action, by rho. Now, rho is now almost the rho you'd use in Lie theory, except every coordinate has an added parameter. So normally in Lie theory, you could choose something like 0, minus 1, minus 2, and so on. We've just added minus delta over 2 to every coordinate. So this is the only dependence on delta in my answer. So I've shifted the origin by something which is a function of delta, but a fairly easy function of delta. And now, of course, I can use that to shift my reflection group action just by moving the origin. So this is exactly like we do in Lie theory, but with a different choice of rho. We know that we can label simple modules by partitions. Now, there's an actual way to construct them, because we can lift representations of the symmetric group. And if you do the normal way of labeling representations of the symmetric group by partitions and lift those representations up, you get the wrong labeling. You have to take the transpose of that. So you transpose the labeling we've just been talking about. If you know any symmetric group theory, you still think in those partitions. And then the theorem says, combinatorially, you check what these two things do, and you find that in characteristic 0, this is a reformulation of the block result. Two weights are in the same block if and only if one is in the orbit of the other. So exactly what you would hope to see in Lie theory. Of course, it's not quite like in Lie theory, because in Lie theory we're working in characteristic P, and this would be an affine vowel group. Here we're working in characteristic 0, and this is the type D vowel group, so that's a difference. And so we haven't yet used any kind of group to describe the dominant weights. Before I go on to that, maybe I'll mention this only depends on the type D, so there's no difference in the positive and negative cases. There's no symplectic case and orthogonal case. And the only dependence on delta is really where the origin is moved to. So it's hidden in the choice of origin. Makes sense for any delta. We've said any integral delta, odd integral delta, for example, don't have any Schur-Weyl duality. So this makes sense for more than just the ones coming from Lie theory. So as I said, in characteristic P, you'd have an affine Weyl group, not a Weyl group. And you have inside that a parabolic, which would tell you which weights were dominant. And then you'd have some casuistic polynomials associated with that, or whatever you wanted to do. Here we still have a parabolic subgroup inside our Weyl group, which determines dominance. So the type A Weyl group tells us what the partitions are. So that's the subgroup that tells us what weights are dominant. And the type D is now playing the role of the affine part in characteristic P. So normally you'd have Weyl group inside affine Weyl group as a parabolic. Here we have A inside D as a parabolic. And that's something we'll come back to in a few minutes' time. What else would you do if you were doing Lie theory? In Lie theory, I said you should draw a picture of alcoves on the board, and you should ignore the lattice of points. And all that should matter for any kind of representation theoretic problem should be which alcove or facet or where you are in the geometry of the reflection hyperplanes. 2 points in the same geometric point, the same alcove or the same wall, should have essentially the same representation theory once you allow for the block to tell you which representative in the corresponding facets to take. So once you know which block you're in, you take the intersection of the blocks with the facets, and which facet you're in, which alcove or wall or whatever, should control the geometry. And you prove that in Lie theory by finding some kind of Morita equivalence between all the intersections of blocks in the same facet. So can we do the same thing here? This is not so surprising. That's easy to do. It's exactly like you might want to do it if you're working in a symmetric group. You project onto a block and then induce or restrict, or the other way around. So you can quickly produce some kind of analogs of translation functors. And if you're in the same facets, some calculations, which aren't very hard, show that this gives you Morita equivalences. Well, almost. You can also look at the relationship between different facets, slightly more complicated, but this is already good enough. So we did this for general towers of the Coleman, not just the Brauer algebra, and gave some conditions for these things to give you Morita equivalences in terms of some kind of geometric action. And these conditions are satisfied by the Brauer algebra. It's not entirely trivial to do that, but we can prove it's true. And essentially, if you're in the same facet, you have a Morita equivalence between the corresponding blocks. I say essentially, again, there's a little asterisk to remind me this is not true, because we're looking at Brauer algebras, so they only have finite many weights. So when I talk about weights for GLN, I've got an infinite set of weights. I'm looking at Z to the n. When I talk about weights for Brauer algebra, I have to cut them off at a certain point because they have to be partitions of n. So I've got a boundary effect. So there may not be the same number of simples in my two potentially Morita equivalent-like blocks. So I just truncate one of the blocks by taking a saturated subset to make them Morita equivalent. So the only thing that goes wrong in the Morita equivalence is they might not be truncated in the same point, so they might have the wrong number of simples. Throw away the simples that don't match up, and you've got a Morita equivalence. So in the global limit, if you like, in the n tends to infinity limit, these should be bona fide Morita equivalences, but we're looking at truncations of them, so we have to be careful. So essentially, this tells us that we can understand the representation theory just by but that we can formulate any answer to the representation theory in terms of the combinatoric of reflections and hyperplanes, and now we should give any answer we like in terms of something to do with the geometry of the hyperplanes and the intersections thereof. So then comes the one part in this talk which is relatively new. So in Lie theory, you might want to use a Castellanic kind of combinatoric. And there you'll depend on your parabolic subgroup and your group which you're parabolic of, which will usually be W inside affine W. Here we've got a parabolic inside something else. We've got an A inside a D, so they're parabolic Castellanic polynomials. And if you go and compute low-rank examples, you can just check what kind of decomposition numbers you get, and they appear to match, and you appear to get filtrations, just like you would expect to do in Lie theory. So we can combinatorially go away and try and calculate Castellanic polynomials. Turns out it's convenient to do this in the infinite limit, because in the infinite limit, it turns out it doesn't matter what kind of weight you consider. Normally in Lie theory, you'd look at regular weights, and you'd associate some Castellanic polynomials with those, and for the weights that are on walls, you'd use translation functors to derive the result. So you wouldn't define a Castellanic polynomial for any weight, you'd define it for a regular weight. If you take the infinite A inside infinite D types, all the orbits are isomorphic as graphs, regular or singular. That's very easy to do by an explicit graph isomorphism. By graph, I mean take an orbit and make a graph structure by saying that two things are connected if they are in the same block and there's a simple reflection from one to the other, the next nearest one in the obvious ordering. So if you do that, you get isomorphic graphs So you can define a parabolic casualistic polynomial for any weight, not just the ones inside an alcove. And since we can just take a sort of finite restriction of that to work out any finite type version, these will be okay. These will tell us the answers in A, n inside Dn. So if we want to do something like Sergel did, so we're not working in algebraic groups. So we should be working in some kind of dual object, just like the symmetric group is dual to the algebraic group. So we always have to remember what the translation is between the various problems. And so Sergel gave an algorithm for determining how tilting modules are made up for quantum groups out of standards. Doesn't matter what they are, except that in the natural setting of symmetric groups and quantum groups, this corresponds to the decomposition numbers for symmetric groups. So if we want to know an analogous theory, it should be telling us something about the decomposition numbers for our standard modules made up of simples. So we can write down some parabolic casualistic polynomials. We can try and give an explicit description of them, and then we can try and show that the representation theory does indeed respect this and give you those decomposition numbers. Various people have described the parabolic casualistic polynomials for the choice A inside D. Ed White and Shelton did it a long time ago. There's a paper last year, I think, doing it purely combinatorially. They're monomials in the parameter Q, so these things would all have multiplicity 1. So in that sense, they're quite easy to calculate. We gave a nice explicit description of them for any weight, regular or singular, in terms of a nice closed form. And then we did the representation theory, and we proved that they gave the right answer. So we do get the decomposition numbers for these algebras from parabolic casualistic polynomials evaluated at 1. And although we can't prove it, all the examples we've done suggest that there should be a filtration of the module where the powers of Q occurring should somehow tell you where you are in the filtration. But that's for another day, since we only have examples on that level.
So this theorem doesn't have boundary effects that you have to...
Well, you both lambda and mu have to exist.
Okay.
So I'm taking that. I always start by choosing my lambda and mu to be weights. So as long as they're weights that make sense for what I'm doing, then everything's fine.
But it doesn't matter if they're sort of close to the edge of the...
No.
Okay.
No. Because you essentially can always make things go smaller. The advantage of using Sergel's procedure is that you start in the lowest alcove and you work your way out. So everything's defined. There's never a problem. It's all okay. So there's still a few minutes left. What else could we do? Well, one of the advantages of this result, quite apart from the fact it suggested using casualistic polynomials and translation functors, is that we could simple-mindedly think about what we might do in characteristic P. So there's a quotient to this algebra, which is the symmetric group in characteristic P. So we're not going to answer the question, because we can't do it for the symmetric groups. But what might we expect, given we know what we know about characteristic 0? So if we were doing algebraic groups in characteristic 0, semi-simple representations, and then we'd... So W indexes the blocks, because there's only one element of the orbit of W in the dominant weights. So as well as telling us the dominant weights, if we then look at the dominant weights, W tells us the blocks. And then the affine extension of that affine Brauer group tells us the blocks. So we've got a block describing group in characteristic 0. It's the type D Brauer group, which happens not to be the one determining dominance. What happens if we do characteristic P? Why don't we just take the affine version? So let's just replace our type D Brauer group by the affine type D Brauer group. We can then have a little play and see what we can say about the representation theory, and it doesn't quite work. What happens is, again, let's assume delta is an integer. Now let's assume we're in positive characteristic. Two simples are in the same block only if they're in the same orbit. But it's not a necessary and sufficient condition. They could be in the same orbit, but not in the same block. So that's not quite as nice, but that's not a great surprise, because even in Lie theory this is true. If you take the symplectic group and look at the symplectic Schur algebra, so not the type A Schur algebra, but something else, that also has the unfortunate property that its blocks are not just the intersection of the blocks for the algebraic group. There's no reason why if you take a subset of weights for an algebraic group and look at the blocks and intersect them, these should still be blocks. They might break up. They do for symplectic groups, and they do for the Brauer algebra. But we have one implication. We have the important implication, the linkage principle. This is the one you'd always use for actual computations. So we can give examples to show it's definitely not a block. And that might also partly be an edge effect. If n is made very large, we can connect our examples together. So in some kind of n tends to infinity limit, it looks like they might be morally blocks. But we don't care too much about that. We have a linkage principle, which is perhaps the best we could hope for as a general result in positive characteristic. And again, it's simple-mindedly done by taking the combinatoric for the affine Brauer group, for the Brauer group, making the affine version, looking at what that tells you, and then trying to find a representation theoretic interpretation of that in terms of elementary combinatorics of the symmetric group and diagrams. There's no Lie theory to explain it directly. is this all a one-off for the Brauer algebra? Well, we had a walled Brauer algebra, which we saw by Schur-Weyl duality should be related to the symmetric group crossed with itself, sigma r cross sigma s. So you could take all the representation theory of the symmetric group and replace it by the products of symmetric groups, which means partitions become bipartitions. So the notation becomes harder, but everything else becomes easier. These are simpler to work with. The nasty inductive arguments become simpler, and you can redo all 90% of what we've just done for these cases. We can probably do all of it, but we haven't finished it yet. So you can go away, you can work out what the blocks are, you can do a combinatorial description in terms of bipartitions. I won't bother to tell you what that is. I'll simply tell you what it looks like geometrically, because it's rather odd. So I've now got a pair of partitions, and I've got to think about how to embed them into my weight space. So obviously they shouldn't overlap, because that's going to be a problem, so I'm going to draw them going in opposite directions. So I'll have a negative part and a positive part, so I'm going to have an origin. So I'm thinking of z to the n as having a sort of negative indices and positive indices. And the one that's in the negative indices I'll draw upside down and back to front, so here it is. And the other partition I'll draw in the normal English way. So I have a pair of partitions spreading in opposite directions. This is the natural choice, because now if I embed this RS algebra into the one higher, I just add boxes at the very top and bottom. So it's not a bad way to go. So every pair of partitions can be embedded into z to the r plus s in this way, which again was chosen to make the answer work. So for the Brauer algebra, we had to transpose partitions to choose the embedding. We then chose a type D Wahl group, and then we had to shift the origin. In this case, because we're thinking of GLN, we're hoping the Wahl group is going to be the symmetric group. So we'll take that. And all we've got to do now is decide how to move the origin around. And again, we have a little play with the answer, take our existing combinatoric that we have for the Young diagrams, and determine that actually we take some hybrid of the ordinary row shift for the algebraic group, which goes down as normal, and then some kind of discontinuity at 0, where we shift everything else by delta. So we shift half of the row approximately by some fixed choice of our parameter, and everything else is the same, so we've changed the origin. And then, as you'd expect, the theorem says that in characteristic 0, the blocks are given by the orbits of this Wahl group on weights. And the characteristic P version of that says that you have an only if condition, which will, in general, not be expected to be an if and only if. Now, the only thing which we haven't done here for the Wall-Brauer is determine the decomposition numbers. I'm very confident that they will be the case of AR cross AS inside AR plus S, but we haven't finished doing the calculations yet. But we expect that we will have parabolic casualistic polynomials controlling the representation theory of these algebras. So in conclusion, as I said, first of all, we haven't done the decomposition numbers for the Wall-Brauer, but they should work. We would like to have a stronger result. We'd like to say that the powers of Q in these parabolic casualistic polynomials should tell us something about the filtrations, not just what the decomposition numbers are, but how the simples are arranged in the standard modules. And really what we always wanted to do was instead have some kind of Lie theoretic machine to play with. So these things are typically quasi-hereditary algebras in characteristic 0, so they have a Ringel dual. The Ringel dual should be a Lie-like object in a much stronger sense, and it's not any of the things that we've seen so far today. What might it be? Well, one thing it might be is a super object. So there's a non-semi-simple object in characteristic 0 which does have this kind of Lie combinatoric, which is conjecturally at least, and partially known to be in Schur-Weyl duality with the Brauer algebra, and that's the orthosymplectic super Lie algebra. Very nice because it combines both types into a single family, and the relationship between the two looks highly compatible. So almost certainly there's a strong link between these two representation theories which would explain part of the Lie-like phenomenon. It's not clear, even if there is a Schur-Weyl duality, that it would answer the question, because, as I said before, you only get quotients, usually. For the symmetric group, we don't know anything about the symmetric group in characteristic P, just because there's a Schur-Weyl duality with the algebraic group GLN. So that doesn't necessarily mean that this will answer the question, but it might explain why you'd expect to see the kind of combinatoric that we do. But it'd be even nicer perhaps if it didn't, because there are lots of other algebras we could have talked about, diagram algebras. And as I say, if you do each one by hand, you very often find that if you think hard enough, you can find an alcove geometry. You can find some kind of group which might not be a reflection group, or at least not a Wahl group. You can find some dominant weights which maybe or may not be a classical choice. And they all seem to be satisfying some kind of, even as far as Sergal algorithm, some kind of parabolic casualistic polynomial calculation or a generalization thereof. So our long-term hope is that somehow we study a variety of these diagram algebras, we might find a more general setting in which this algebraic Lie theoretic machinery can be applied. Thanks so much for your time.
Questions?
Yes.
Question. If you use sort of an Arakawa-Suzuki duality for the Nazarov-Wenzel algebra, you get decomposition numbers from that Schur-Weil duality for the degenerate Wenzel algebra, and the Brauer algebra should be a quotient of that.
It should, yes. There are some, well, that's true. It's not quite clear how the combinatoric goes through, but more importantly, this is a very elementary calculation. I think I would claim this is a simple proof, because all I'm using in characteristic zero, which is all we're going to get from that, is symmetric group character facts plus some inductive steps and some very easy calculations.
But does it match?
I couldn't see the matching, or more seriously, so I really looked at your paper with Orellana about the BMW paper and considering the limits in there. It wasn't clear to me to get them to match. That was mainly because I was sure I was following the combinatoric. I think it should match. It has to match because this is the theorem. The characteristic P stuff, though, I don't see how to get that in this way because of the parameter choices. And I'd be a little bit nervous with the BMW even at roots of unity, where again I expect this analysis should work, and you have to be slightly more careful about what you know about the affine Hecker algebras at roots of unity or characteristic P. So you may be able to get some of these results in that way, but I like not to, simply because this should work in more generality. And for algebras that don't arise at all with this family, not just for algebra.
So you said this thing about Morita equivalence for weights on the same facet.
Yes.
What happens if you change delta?
If you change delta, then we'd like to think that there were some kind of equivalences, but this would be very hard to show. I mean, it'd be like proving the ballistic conjecture, wouldn't it? I mean, you'd like to say something similar in algebraic groups and characteristic P for P sufficiently large, but we don't have to do that. There's slightly more hope here because there are ways of changing delta. So a physicist's trick, which I've never really understood why the physics behind, but which works, is if you've got a diagram algebra, you can just draw twice as many strings. This is called grading in physics. And if you do that, you get an algebra which is a subalgebra of the 2n algebra, because you've got twice as many strings, but it's essentially isomorphic to the old algebra because you just double all the strings. And the only thing that changes is the loops become double loops because there's two strings, so delta becomes delta squared. So there are ways of relating, and then you can do other tricks to do others. So there are functions you can do between different delta values that are perhaps easier to see here than they are in, say, the symmetric group or the algebraic groups. But they're not strong enough, and I don't see another way to work which gives general delta dependence. I can't see.
Do you know any small examples with, say, two different small integer values of delta where you have Morita equivalent blocks in the different?
If you do computations, everything seems to work. I can't think of any restricted name. Maybe delta not zero. But essentially, when we do examples, the delta values, nothing should really matter. All the calculations that you do, well, because of the way the answers are formed, they can't. Anything that we've seen can't be different from different values of deltas because all we have are reflections and the hyperplane combinatoric. Everything we've ever done translates into the hyperplane combinatorics and hence can't depend on delta. But that doesn't prove yet that these things are anything like root equivalence. All we know is the decomposition numbers are the same, but that might not be enough.
Other questions? So maybe let's thank the speaker again.